No, 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 no.
I can't hear you. Are you hearing me? I think you are muted here.
Oh, sorry. Just a minute, Eric.
Okay.
I made something wrong, but I okay.
I think the problem is I am the host of the call.
Yeah,
Should
no,
I
it's
leave
just
and enter again?
no, no, it's okay. It's just because I put the wrong name, but I think I can change later. I don't know.
Okay.
Just stop sharing your screen, please. Just for a moment.
Stop sharing.
Okay, thank you. Just a minute. Let me see here. No. Oh, yeah. Okay. I don't know how to stop to believe. Okay. Alive, it's started with problems, but it's okay. So let's start. I changed the name later because I put the wrong name here. So hi, everyone. Hi, Eric. You can listen?
Hi, Tainara. Yes. Hi, Tainara. Hi, everyone. Okay.
Okay. So today we have Eric here. It's a great pleasure to introduce him. Eric, it's a Brazilian materials engineer, has a master's degree from Unifesp, and is currently doing his PhD in polymer science at UFSPA, one of Brazil's most respected institutions in material science. Eric's research is at the forefront of material science, covering areas such as 3D printing, electromagnetic behavior of materials, and nanotechnology, with a specific focus on polymer nanocomposites based on graphene and carbon nanotubes. I have to read because it's a lot of things. So I'd like to thank you for accepting this invitation and this challenge. I know it's speaking English for us, it's a little difficult, but I know you're gonna be very great. So when you want, you can start.
Okay, Tainara, thank you for the warming presentation. Let me share my screen here. Are you seeing my screen? It's okay?
Yeah, yeah.
And the
Fine.
pointer as well?
Yeah,
Or no?
yeah.
Okay.
Everything okay. I will
So
mute me, but when I will speak, I will dismute.
okay. So good afternoon, everyone. I'm Eric dos Anjos, a 20-year-old Brazilian. And to start, I would like to express my gratitude to Tainara to extend this wonderful opportunity here to share some things about this fascinating world of polymers. Okay, so today we're going to talk about polymers. Why are they important for 3D printing, and what are they exactly? Okay. So to start and provide some context, I'm currently, as Tainara has said, pursuing my PhD SCAR, okay? And the focus of my research is on developing new materials for 3D printing that have, so this is why I have this small background about 3D printing and how polymers behave in this context, okay? Here are some contacts if you want to enter in contact with me before the presentation. And at the end, I will have some special recommendations for you. So I'll really advise you to stay upwards the end of the presentation. Okay, so let's jump to the context. Our presentation is structured to provide with a quick overview of polymers, okay, their architecture and their relevance to 3D printing. And I hope that by the end, you all have a clearer understanding of the distinctions between polymers and how their chemical structure affects their behavior, usability, and properties, okay? Just a small introduction. Just a little thing, our focus here in the context, I will try to bring the e-NABLE products, prostheses, and orthoses, trying to make some links here, but I'm not a healthcare professional, so I'm not so familiarized with this thing, okay? Back to the polymers. Before delving deeper in the world of polymers, I think it's vital to recognize that why polymers matters for 3D printing. And to start to construct this knowledge, I would start with a question. Are all plastics or polymers the same? What do you think about it? So to prove that polymers are not the same, I will give some everyday items examples here. For example, safety goggles, a pool ball, and a Matters sponge. The three products are made mostly from polymers. However, they have really different characteristics. A safety goggle is rigid and transparent. A pool ball is almost an elastic solid, while in the other hand, a Matters sponge is a really soft material. So why polymers can be so different from each other? This is one of the questions of this presentation. From the previous question, an even higher important question rises, that is, should I use the same material for all the prosthesis parts? What do you think about it? I think most of you think it's the best to use the same material. Some of you diverge in this opinion. And this is a question that we will go back again at the end of the presentation. Okay, so now, knowing that we are here at e-NABLE and the focus of e-NABLE is 3D printing, I think most of you have contact and experience in 3D printing. So I'll just have a quick review of some fundamental concepts of 3D printing. So at its core, 3D printing is a manufacturing process, a family that builds any object, trying to construct the object layer by layer. And the idea is always based on a digital model. So 3D printing is really advantageous when we look for versatility, when we look for maximizing the material, so minimizing material wastage. And the most strong characteristic of 3D printing is the customization capabilities. Yes, so for medical devices and other industries like aerospatial industry, customizability is a really strong focus of 3D printing. Here we can see that 3D printing is actually the best cost-effective manufacturing technique for lower quantity prices, so customizable prices. One of the main applications of 3D printing is medical applications. In medical application nowadays, 3D printing is used for prototypes, tooling, teaching aids, and in case of e-NABLE for end-use parts also. And the great advantage for 3D printing in this case of medical applications is customization. However, medical applications have unique requirements. The most difficult to achieve requirement for polymers is sterility, because for sterility we must undergone some severe physical conditions like higher temperatures, radiation exposure, chemical exposure, for example. All those can be harmful for the polymer structure in some cases, so not all polymers will satisfy sterility. Other requirement for medical applications is traceability, so not all polymers also are commercialized to be traceable. It's another difficult to match requirement. And the most easy to match for 3D printing is organic shapes, independent of being a polymer or other material. Moving forward, we should understand that additive manufacturing encompasses a range of processes involving various materials and strategies. In this presentation, I'll focus in just a polymer material. So the most techniques that apply most polymers are vat polymerization and material extrusion. Vat polymerization is commonly known as stereolithography, applied this family of additive manufacturing, while material extrusion, the most known process is FDM or FFF, the one that you use in e-NABLE. So these two processes mostly apply polymers. This is why we're going to focus in polymers and especially in material extrusion in these presentations. However, we have other additive manufacturing families that can apply almost all types of materials, ceramics, metallics, composites, and etc. Finally, let's start with this brief foundation of 3D printing. We can delve into the core of presentation, understanding the nature of polymers. So polymers can be defined in various ways, okay? The most common definition is defining polymers as long chains or networks of repeating molecules, also called macromolecules. The polymers can be also called macromolecules. And what does it mean? It means that we have the same structure repeating multiple times to form the polymer itself, okay? There is a big field to study polymers that we call polymer physics and chemistry. However, here I'll just give a brief introduction about this field, the main aspects that you have to take in mind to understand better the polymer physics and chemistry, okay? And I think the most easy way to approach this is based on the materials engineering point of view of polymers, that we base the classification of polymers on their properties. So we can have three major distinctions of the polymers based on their properties. There are thermoplastics, simply called plastics, thermosets that came from liquid resins, and rubbers, okay? When you talk about thermoplastics, we have these two. They are the most used and the most known and simplest thermoplastics. They are polyethylene and polypropylene. These materials are just constituted by the simple structures here, repeating multiple times, forming long chains and independent chains. Thermoplastics can be fused or melted and solubilized in some solvent. This is why they call thermoplastics. They can have plasticity when you have temperature, for example, while thermosets are a different type of polymers, more like a network. They start from liquid resins here, small molecules that start to reacting with each other, forming bigger molecules, and finally a 3D network that cannot be fused or melted, neither solubilized in any solvent without breaking the chemical bonds here formed. Okay, they were called thermosets. They are setted. Focus here more in thermoplastics. I think is the material that we use more for the e-NABLE end of use applications. We can have different kind of thermoplastics. If you have one repeating structure like polyethylene, we call it homopolymer. However, if you have more than one, we can make different type of structures called copolymers. And copolymers can have different architecture and structure. These two terms here is how the molecules bound to each other to form the polymer chains. And we can have different types of copolymers, alternating or block, for example. We can have different shapes of polymer chains. This is important because, for example, with the same homopolymer, for example, polyethylene, if we change the chain configuration, we can have different properties at the polymer in the end. For example, linear polyethylene generally comes from high density polyethylene, which is tougher and stronger than a branched polyethylene that we call low density polyethylene that has longer branches here. So just changing the configuration of the chain, we can have different properties. We can also have different types of polymers bounded together. In this case, we have grafted copolymers that we have one backbone of one polymer and grafted chains of other types of polymers. This kind, for example, is the same that we see from ABS that I will talk about a little bit later. It is also an example that we can use this type of technology in a real-world application, a material that's already commercial. Moving forward, we can talk about a little about the structure and organization of polymers. So polymers in the solid states can also be differentiated in two categories. We call amorphous and semi-crystalline polymers. When we picture amorphous polymers, we can imagine a plate of pasta. There are many strains intertwined and connect to a few others, not chemically, but just physically, just anchor themselves. And when we pull one string, you can move many others around it. So it behaves like a solid in room temperature, for example. And we have another category that is semi-crystalline polymers. Semi-crystalline polymers have this crystalline regions called lamellae. This lamellae can be pictured again as a culinary example, as a round noodle, where the same strings are folding and bending into each other to form a more packaged, more regular structure. And this structure confers to the amorphous matrix many different kinds of properties. So it's more rigid, it's more resistant to solvents, to gases, for example. And generally, these polymers can arrange the crystalline and the amorphous regions in many different structures. And an example is these spherulites here, which are a regular circular structure for lamellae and amorphous region. The last part here that I will discuss about polymer architecture is the molecular weight is also really important for polymers. So having the same chemical structure repeating different times, which is indicated by this number here, N, which is the polymerization index, we can have different properties. I will show a practical example. For example, with this structure of the polyethylene, if we repeat just a few times, 12 to 18, we can have paraffin wax, which is a small molecule, not classified as a polymer, and have a lower temperature of melting point, okay, around 50 degrees. If we increase this polymerization index to a higher number, for example, 3,000 to 4,000, we have HDPE, which is a polymer in this case with a melting point around 110 Celsius degrees, almost the double of the paraffin wax, and has excellent mechanical properties, tensile strength and modulo. If we increase even more the polymerization index, we will have a polymer called ultra-high molecular weight polyethylene that is virtually no meltable. So you destroy the polymer before melting it in a polymerization index really higher for 4,000, for 400,000, for example. This polymer has extremely good mechanical properties, however, is really difficult to process, for example, so it's not much commercialized. The explanation for this changing behavior, just changing the polymerization index, can be understood by the entanglements, the interactions between longer chains that are favored than smaller chains. For example, with longer chains, we can have more knots or bonds between polymer chains that make this material tougher or harder to melt, for example. Another important thing, consider molecular weight, is that known that polymer materials are not made from the moleculars with the same molecular weight. We generally have a distribution. The distribution can be narrow or wider, and this change can actually affect the rheological behavior of the polymer and how it behaves mechanically and etc. So it's another important factor here. Okay, so with this just brief presentation of the main characteristics of polymer physics and chemistry, we can dive deeper in common thermoplastics focused in additive manufacturing. So when you imagine plastics for additive manufacturing, especially for FFF process or FDM processes, we generally can classify these thermoplastics based on their properties. Again, in this case, we can divide them based on their temperature of application, maximum temperature of application, but it also stands for price or mechanical strength, for example. In this classification, we can classify these plastics as standard, engineering, or advanced plastics. Standard plastics are applicable just at room temperature up to 100 degrees. If you need a material that resists more to heat, we can have engineering plastics that resist up to 150 Celsius degrees. And if you need a really extreme condition, like up to 350 degrees, we will need an advanced plastics. It's important to notice that the price is other characteristic that varies a lot with the type of polymer we are talking about. So for example, when you compare a PEK here, which is an advanced thermoplastics, it could be its cost is around $400 to $700 per kilogram, while when you compare a standard thermoplastic like ABS, we have this price really lower here than $17 to $25 per kilogram, for example. This is just an example. Okay, Tainara?
Eric, here in Brazil, we have all of these materials or not?
In Brazil, we don't synthesize most of this material, but you can buy it. You can find some.
It's very expensive here.
Yes, it's more expensive than here because you have to pay taxes for the exportation of this material. For example, PLA, I don't know if you have a national company that produces PLA. I think we don't. So when we bought PLA to make, we have synthesized the plastic. Do you know some, or just produce the filament?
Oh yeah. Okay. Just the filament. I think. Yeah, it's different.
Yes, because I tried to buy PLA once for a project here, a medical grade of PLA, and we pay around $1,000 for a kilogram. Because
really?
because you have to buy in outside of Brazil. I think you buy from USA, and Nature Plastics, I think it's France or USA, and you pay
here in Brazil, the things are very expensive.
It's really expensive.
Yeah, so it's
Yes,
because
I know
I never
polyethylene
see
and
all the
ABS we have Brazilian.
polymers. Yeah. Okay. Thank you.
Okay.
You can continue.
Okay. So another thing that's important to think about these different types of polymers is that one size doesn't fit all. So each polymer is unique. It has its own balance of properties. So here, for example, I have a visual way to compare the most common polymers based on the ease of printing, visual quality, elongation, impact resistance, and heat resistance. So if you look into PLA, for example, that is the favorite for almost everybody. It has excellent visual quality. It's really easy to printing, and it also has an intermediate impact resistance. When you look to ABS, on the other hand, we have good resistance. However, it's really harder to print and may also not have a really good visual quality, for example. So each polymer has its unique balance of properties. Now let's now take a closer look here. The main characteristics of each polymer that I show in the last slide. And we can see that each polymer has its own set of characteristics. For example, when you talk about the application temperature, or the temperature the material will be used, yes, this is limited for two characteristics temperature of each polymer. So polymers that are amorphous are characterized by its glass transition, and polymers that are semi-crystalline are characterized by its melting point or melting transition. Let's take a simple example here. If you look to ABS, ABS is an amorphous polymer, so it doesn't have a melting point, just a glass transition. And its glass transition, it's around 800 Celsius degrees. This is why ABS can be applied just up to 85 Celsius degrees at maximum, because it will start to soften at higher temperatures. On the other hand, we have an advanced plastic here, PEK, which can be applied up to 350 degrees because its glass transition is around 400, and its melt transition is around 500, for example. So it's a polymer that resists really high temperatures. Okay, the same line of thinking can be applied for the mechanical properties as well. For example, ABS has an ultimate tensile strength around 45, while PEK has more than the double of the ultimate tensile strength, around 800, for example. I recommend the ones of you that are more interested in this type of differentiation, this reference here that is really good and focused on 3D printing for clinic applications. When we talk about polymers for 3D printing, in general, we have significant benefits for applied polymers. Polymers are actually the most cost-effective materials. They are versatile. We can have different kinds of polymers that can fit in almost any application. They are light. They're most recyclable in the case of thermoplastics. Some thermoplastics are even biodegradable, okay? And the strongest characteristics for polymers in 3D printing is their lower energy consumption or processing. This is explained why we can have a 3D printing of polymer at home. However, if you need a metal 3D printing, probably you cannot have it at home because it will require a higher amount of energy to melt the metal or to fuse the metal or to have a laser. So this is why 3D printing of polymers can be so homemade, different from other types of materials 3D printing. So now I bring here examples of the most applied materials, some advantages and disadvantages of applying each one, and their chemical structure to understand a little bit how these things are connected. So starting with ABS, which is acronyms for acrylonitrated butadiene styrene copolymer, we can have that ABS has these three repetition units here. This repetition in the polymer, as I said earlier, have this grafted design. So we have a backbone here of polybutadiene with grafted chains of acrylonitrile and styrene polymer. The blue chains here represented. And the ABS matrix is like an heterogeneous material. ABS, we have characteristics of each one of those structures. So for example, acrylonitrile here, this structure compared to ABS, thermal resistance and chemical resistance. This one, polybutadiene, will convert to ABS impact strength, for example. So this is why ABS has these types of characteristics. ABS is a really versatile polymer. It can be applied for automotive parts, electronic housing, toys, and prototypes, for example. And it's one of the most used polymers for 3D printing, okay? There are some disadvantages of applying ABS. For example, ABS is really prone to warping. So if you don't have a heated table, it's really hard to print ABS. And if overheated, it might emit fumes. So it's a versatile, however, those are some disadvantages of ABS. Okay, Tainara? You can just open your microphone.
Back to ABS, please. Just two questions. When we go to a store with we have toys, kids toys, we can see in the materials ABS. And I want to know the difference between the ABS we use in 3D printing and the ABS we see in these kids toys we see in the stores. They have difference?
Yes, they have difference. This is a really good question, however, a really hard to respond question, because you can see here that ABS is formed by 3 structures, okay? And we have different polymerization index for each one. So we can have really multiple types of ABS, just varying the content of each one of these 3 structures, okay? We can have ABS more softer, more heat resistant, or more chemical resistant, or more or less expensive. For example, just balance these 3 components in the ABS structure, okay? I think the main difference between the ABS for 2D printing and for toys in general would be their purity probably. So I think ABS for toys must have some safety guarantees, like have no harmful chemicals in their composition, has less harmful chemicals in general. While when we're talking about ABS for 2D printing, we probably have more additives, for example, plasticizers and other additives that are not good for children, for example, put in mouth and etc. So I think these grades can be different in composition and also in additives, what you put in the polymer to make it more processable. Did you got it?
Okay. It's
A little bit?
yeah, it's dangerous make kids toys with ABS 3D printing because they put everything in her mouth. So it's something dangerous for them or not?
In general, I think it's not be so harmful. However, we've considered that maybe, I don't know exactly, there are some plasticizers or any type of molecules that could be harmful for the children. You don't have this guarantee. Generally, when you are searching for a grade, seeking food applications or seeking medical applications, you go to those special requirements like traceability, like sterility, like purity. So 2D printing materials doesn't fit those requirements. If they are fit those requirements, they probably would be expensive, more cost, you know?
Okay, and the last question about ABS.
Okay.
When I treat ABS with acetone vapor, does it still have the same resistance or it's different?
The acetone vapor, acetone is actually a really good solvent for ABS. This is why we treat this polymer with acetone, not PLA, for example. It's just worked for ABS because it's a solvent for this polymer, okay? And when you do that, I think most of the cases we're thinking about aesthetic purposes. So it's just superficial treatment, not inside the part, you know? So if it's just superficial, not so harmful for the mechanical properties. However, if you exceed the time or exceed the quantity of solvent, for example, you can actually harm the polymer properties, for example. So it's just a balance to do correctly and just for the surface, not for the inside of the polymer structure. Okay?
Thank you. Okay, thank you.
No problem. Your questions are really good today. I like ABS, is my favorite. Is the polymer that I choose for my PhD.
You know, I hate ABS. So I have two questions because I don't like ABS, but okay,
Oh,
thank
no
you.
problem, no problem. The next polymer here is PLA. PLA is a biodegradable and environmentally friendly choice for 3D printing. This materials has also advantage of being low odor and non-toxic. It's easier to print, so it's low prone to warp, okay? However, we have some disadvantage for PLA too. PLA can be brittle and less resistance than ABS, around 60 Celsius degrees. This is why you can thermoform PLA printed parts, okay? Another disadvantage of PLA is that it might degrade over time, but just in certain conditions. It's not so easy to degrade in application conditions, okay? A curiosity here about PLA is that PLA has two optical isomers, okay? So depending how the molecule is conformed, you can have L, lactic acid, or D, like PLLA or PDLA, we call it. Commercial grades are generally most from PLLA, that is less brittle and easier to process than PDLA, but some grades can have a balance of both structures, okay? Now we have other two standard polymers here, polyethylene, that I call a lot in this presentation. This is the simple structure. Polyethylene is actually in our daily lives, for example, in plastic bags, okay? This polymer is versatile, has excellent electrical insulation and chemical resistant, is really easy to process for traditional processing techniques like injection molding and extrusion. However, this polymer is rarely used for 3D printing because it doesn't have a good adhesion for neither in between layers, neither in the 3D printing bed. So we can have really challenge for trying to print PE, for example, due to this poor layer adhesion. Okay, this is why this polymer doesn't thrive too much in 3D printing. Another polymer really similar to polyethylene is polypropylene, with just this methyl group here, substituting a hydrogen atom. This makes polypropylene harder and stronger than polyethylene. It's less flexible, but it's also stronger. Polypropylene is applied for food containers, for example. Automotive parts packing is also a really versatile polymer, and also really applied in the industry in general. However, this polypropylene has the same disadvantage of polyethylene. Its poor layer adhesion is really hard, turns it really hard to print. So it's limited for use in 3D printing applications. This is why we don't see PE and PP in 3D printing as much as we see PLA and ABS. Continuing, moving forward, we have ASA, which is similar to ABS, just with a little difference between instead butadiene, ASA has an acrylate group here, as shown in this chemical structure here. And this difference between ASA and ABS gives ASA an advantage to be more resistant to UV radiation. So ASA could be a more suitable polymer for outdoor use because it has a better weatherability. So it can resist better to UV, to the sunlight, for example. For the same chemical structure, they have almost the same disadvantages for printing. So they may require a heated bed for better adhesion. It's really hard to print ABS or ASA in a cold bed without heat. And they are both prone to warping. So they are a little harder to process than PLA and other thermoplastic polymers. The last standard polymer here we can see is TPU. TPU is a standard in some cases also in engineering plastic. TPU characteristics is high flexibility, exceptional impact resistance, good abrasion resistance, okay? It's applied in industry in general for footwear, phone cases, seals, gas tanks, and sporting equipment in general. It's extremely flexible and stretchable when you're looking for an application or a printed part that looks like a rubber behavior. We should use TPU. However, TPU has low heat resistance and might prone to stringing during 3D printing. I think among all those thermoplastic polymers that I will talk here today, TPU is the most complex one because TPU is not just a simple chemical structure. It could actually be many different types of polymers together. For example, here I just showed the characteristics of TPU is this reaction between isocyanate and an alcohol group here in the end of the chain, forming a urethane chemical bond. However, this blue chain here represented could be many different types of polymers: polyester diol, polyether diol, different types of polymer diols. So this is why it can have many types of different structures here in the blue chains represented. And those blue chains are generally soft phases that are bound together by those hard phases like this one. And this is why we have the rubbery-like behavior. However, it behaves thermically like a thermoplastic, not like a rubber. Now entering the engineering polymers, we had PETG, PATG, which is polyethylene terephthalate glycol modified. Known by its excellent adhesion, strength, impact resistance, also can provide transparency and clarity, okay? This material is generally used for water bottles, food containers in industry in general, and for 3D printing can be used when we seek functional and clear printed parts. However, PETG requires a heat pattern for adhesion and has moderate warp. And we also need a 3D printing that can achieve higher temperatures in the nozzle to print this kind of polymer in almost all engineering polymers. Polycarbonate, my favorite of the engineering polymer, is represented here. Polycarbonate is the polymer used for safety air glasses, like safety goggles that I showed in the beginning. So its main characteristic is being transparent. So it's actually excellent optical clarity, okay? Polycarbonate also possesses an exceptional strength and toughness due to its chemical structure that has its aromatic rings here in the backbone of the polymer, which make this polymer stiffer and stronger than the other polymers, and can resist for higher temperatures. So we can apply polycarbonate up to 140 Celsius degrees, which is a little higher than the other polymers. Polycarbonate is used for many applications in daily life, like automotive components, medical devices, eyewear, aerospace parts, etc. However, for 3D printing, polycarbonates has some disadvantages that are, it will require a higher temperature 3D printer, and is also prone to warping. So it's not so easy to 3D print polycarbonate. Another engineering polymer that is applied in the industry heavily is polyamide 6, also known as nylon 6 in the industry. This polymer of the engineering or standard polymers that I sit here can be understood as the polymer which has the higher toughness and higher strength of all. The strength and toughness of polyamide comes not from exactly from its backbone, however, for its hydrogen bonds. So polyamide can make hydrogen bonds between different polymer chains that make this polymer specifically stronger than the other polymers. This is why polyamide or nylon 6 are so strong. It's applied in industry in many ways for gears, beers, brushing, structural components, for example. For 3D printing is applied for more advanced parts and when we seek for durable parts or parts that require much higher mechanical strength. The great advantage of polyamide 6 is that it absorbs moisture and it can change its dimension stability. So as we talk, polyamide 6 can make these hydrogen bonds here, and water also makes hydrogen bonds. So this is why these two can be so close related and interact chemically with each other. This is why polyamide 6 absorbs moisture. And for printing, we have to take care with moisture, have a heated chamber, and also a 3D printer that achieve higher temperatures. I bring here one example. The last polymer that I will talk today is polyether acetone. This polymer is an advanced thermoplastic. As you can see, it have even more aromatic ring at its backbones than polycarbonate, for example. So it's even stronger and can uphold even higher temperatures. Okay. This polymer is known by its exceptional mechanical property, its exceptional chemical resistance, and its high temperature resistance up to 2060 Celsius degrees. Okay. Some disadvantages of 3D printing PEK is that it requires a specialized 3D printer and also needs its higher cost compared to other types of filaments. So it's a expensive polymer. Here, just a brief perspective about, oh, Tainara, just open your microphone.
Sorry.
And
No, I prefer
raise your finger.
so raise my hand. I just have one question or two about the polymers you bring to us today, because of the prosthesis and orthosis. We can, it's we can wash this with soap and water, these polymers, or will change anything, or how long they can accept the the clean, or how it works.
It's another good question, and also another question that's hard to answer. But if you think that water and soap could actually harm the polymer or solubilize the polymer or attack polymer in somehow, I think they can't. If the all polymers here are soluble in water, for example, we have much problems in application because, for example, you have a automotive part of ABS or some polymer and it starts to rain, your polymer melts down and you lose your parts. It's not be applicable. So most of the polymers that I see here, you can wash without problem. They can uphold many washes, so you can wash many times without harmful the polymer actually. I think you have to take care about how do you dry your 3D printed part. So
Yeah.
if you dry with a high temperature, you can actually change the polymer. You see that polymers can be applied just in a range of temperature. So if you exceed the range of temperature, and also how do you wash it? So if you use high pressure, if you use, for example, a sponge that have abrasive components, it can harm the surface of the polymers. Also, if you use some kinds of chemical like chlorine or other types of chemicals, you can enter the polymer and be liberated before you dry it, so you can liberate the chemical before the harmful chemical. So some aspects you have to take care, but just water and soap, I don't see problem to wash your
And sweat.
3D printed parts.
And sweat,
Sweat
it's
is
okay too.
also a not so harmful chemical, not so harmful solvent. Do you know, it's just water with some salts, okay?
Yeah.
So most of
Okay.
the commercial polymers won't be harmed for water with some salts. However,
Okay.
PLA and special biodegradable polymers like polycopyl PCl, for example, or PHBV or PHB, I think might be attacked by water or bacteria in your sweat. However, these
Okay.
polymers that are commercial are really resistant of water and other types of solvents here. Even polyamide
Okay.
here. Polyamide can be applied in contact with water. However, we have to keep in mind that it can affect its dimensional stability. So it's better to have it saturated with water in the last dimension that you need.
Okay. And which of these materials is most suitable for contact with foods?
Oh, I think none of those are great foods exactly. However, by what I have read, I think polypropylene will be good for food, and also PHG here, PHG is recommendable by food, but I don't think those are food grades exactly. So it's better when you're applying something to the printing for have a contact with the food. It doesn't have direct contact. It's just support something that will touch the food. The
Yeah.
packing or something keeps protecting the food from the part.
Okay.
Okay.
And just for finish this subject, in the chat in YouTube, Eric Buber say in about ABS, of course. In my university, say 3 people won't let me use it due to the harmful particulates discussed in the literature.
Oh, okay. So
Yeah.
I think this is a kind of a misinterpretation about ABS because, as I said, ABS was just free to the environment some harmful particles if overheated. So if you're working in the temperature of processing, it's okay, it's not harmful. It can have a strong odor. It's a disadvantage of ABS. You can smell something, but it's not harmful. It's actually a really small quantity, and the polymer in itself is not breaking or freeing so much of this molecules, this harmful molecules. Okay. This is why we use ABS in industry, and when you're working for example, an injection molding facility that injects for automotive parts, for example, that I have worked in one with, you don't have to use a special face wear or something to work with ABS. It's just a smell. It's not chemically harmful for you. Okay.
Okay. And he say, I think the bigger food problem is the method of printing. Too many layers and pockets to hide the bacteria in. So that's a big problem too.
Yes, but we know that we can adjust the printing parameters to make a solid, almost solid piece that won't leakage. Do you know? We can print a mug or a cup of 3D printing. So it's
Yeah.
just adjusting the parameters. But as I said, the filaments of 3D printing generally are not food grade. So it's best to have another part to enter in contact directly with the food, not the
Yeah.
3D printing part itself. Okay.
Okay. Okay. Continue.
Thank
Sorry.
you for the questions. From the YouTube. I like these questions. Okay, so just fewer ending slides. So this is some perspective of new materials for 3D printing. So I think the most important tendency that we have new materials for 3D printing for FFF in FDM are nanocomposites or composites that we have another material add to just add some functionality for this material. Doesn't change its core structure, so it keeps the matrix properties to being processed. So for example, here we can add, my PhD research is basically this idea. So I mix graphene and carbon nanotubes to ABS and try to make it electrical and electromagnetic responsive. But you can actually use bioactive molecules for making it better for healing. Tissue engineering also applied lots of these ideas, not with ABS, but with other biodegradable matrices. So I think this is the most strong tendency. Just have the same matrix that we have already, but adding new materials to have new kinds of nanocomposites with different properties. Here are some key tips for polymer 3D printing. So I think my core of this presentation, my main focus is that you have in mind these three main tips is that each polymer is unique. So you have to have different processing parameters, different ways to store your material, comparing the unique characteristics of each polymer. Another important thing is always avoid moisture. So always try to have a moisture-free environment. Try to store your filament in a Ziploc with some silica in it to absorb the water. And we should always tailor the parameters for each polymer that you use. So for example, if you're using a polymer that requires a bed heated for better adhesion, use a bed heated 3D printer. If you need a material that requires a higher 3D printing temperature, using a printer that achieves a higher temperature in the nozzle. And also we have to adjust the 3D printing speed and other parameters to try to match the parameters with the polymer that we are using. Tailor both things together, the polymer and the process. Here I have some recommendations. So here I just give a brief explanation. My English wasn't so good, so I think you should looking for, if you are interested in more about polymer sciences and processing, I'm suggesting this discipline online is a graduate level of discipline from Professor Nicholas Vogel, which is a wonderful professor, and all his content is free in YouTube. So just searching for polymer science and processing for Professor Nicholas Vogel, and you can find a really good discipline, scientific and applied discipline of polymer science. I really recommend those of you which are interested in polymer processing science to watch his videos about polymer science. Another thing that I recommend here is a 3D printing medical industry, the video, which is from Go Engineer. This video has some medical grades. They are actually sellers of 3D printing materials, so they will recommend some medical grades. some different types of ABS that can be applied for medical uses, for example. And it's really interesting. So I suggest you to watch this video, especially focused in the materials suggested by them, the materials they sell. Finally, to finish the presentation, Tainara, I would like to just discuss a little bit about the applications that e-NABLE. What do you think about the answer that about the question that I raised in the beginning of the presentation? Should you use the same material for all the prosthetic parts?
Yeah, we always talk about that when of the day we first met. I think you always talk about that.
Yes.
And that's why I really loved about the subject of polymers because it has a lot of things in this field. It's really amazing. And that's why I call you here. And I already talked to you how I think PLA it's the best option for the prosthesis. Not for all, but this part here of
Cup here.
the yeah, this gauntlet and the palm. I need to thermoform this gauntlet, so I need to put in water or use. Um, I always forget the name in English. It's this soprador térmico.
Thermal,
It's the
thermal
yeah,
source,
it's
thermal
like
heater.
the yeah, yeah. It's like woman using the hair. So we need to heat this and when to thermoform and make this form because they came like this. I have one here. They came like this and we need to thermoform with water heated or anything. And for PLA, it's better for make the adaptation of the anatomy, and I like a lot. And sorry, Clotilde has this thought.
No problem.
She's ready. And when I talked to you about that, you asked me, but the palm you can make in ABS, but I don't think so because we make this with these both together, and because
Mhm.
of the heat, they both like match. They make a match with this heated, and so I think the palm and the part we need to thermoform should be in PLA. So for me, just these parts. For fingers can make with ABS, pins you can make with ABS or PT or what do you want to do. But these two parts, I think it's better PLA.
Okay. And have you have any problem with joining different polymer types? For example, have you observed if you when you have a part of ABS with a part of PLA, you have some kind of trouble, long life applications, for example, they start to
So
no
they just
no
need to be good printed and just these two parts that I say. If one it's Pele and another it's ABS, they don't have the match, so
you
it's
have
not
the
so
problem
good.
too.
Yeah, true, because ABS it's very resistant, have a good resistance of for heat,
Yes.
so it's very difficult. But the other parts, ABS get a better quality than Pele sometimes. So the other parts, it's even better to do with ABS. I don't like ABS, but I know he's very good.
I do remember when we are when I was helping you in your master degree when you were studying mechanical properties of the 3D printing parts. Most of the time, it's not the material case, yes, is how do you print? Because if you have any printed defects, your mechanical resistance goes down below, goes to zero, yes.
Yeah,
So I think printing
yeah,
quality is most important than the material sometimes when you're thinking about uh,
yeah,
use applications for persons, yes.
yeah. It's because the procedures is like a puzzle. If you buy a puzzle with wrong pieces, it's you can play. So it's like the procedures. If you take the procedures and take everything and just put together and it's not good, don't work well. So sometimes you can see some people with the procedures and don't close the hand a lot. So sometimes just come to here. No, not for here and everything. So we need to print with quality. I think we need to understand the polymers and 3D printing and the materials and everything to make a good prosthesis.
Excellent, excellent. This is the conclusion here, I think.
We
Excellent,
have
Tainara.
one question in the YouTube.
Okay.
Two questions actually. Any suggestions on the best FDM polymer for skin contact?
Sting.
Skin,
Ah,
pele.
skin contact. Oh, I
Yeah.
think in case of the skin, we can think about softness, maybe. Because I know in prosthesis you make the rigid parts and then you have something inside to make a softer contact with the skin, yes?
Yeah,
So
yeah,
I think when I'm working with a person, we must think about how does it felt in the skin. So ABS, PLA, all those polymers went to the printing, they will feel some kind of rusty, I think,
yeah.
rigid, some scratchy.
I think he
So
talked about some printing things. We can put some anything at all inside. Like I put I really don't know the name in English, so sorry guys, but EVA. I say something like this sometimes and it's almost the same name. And sometimes we print and we can put this softly thing to help with the skin. So I think it's this question, like if it's dangerous to put something
no,
directly
in
with the skin.
contact, uh, all those polymers are actually really stable at room temperature and most of the conditions that a person will have. So I don't think any of them could be harmful for skin contact. I think you have more problem with nickel in your jewelry, for example, in allergies or etc., than you have if you have some polymer in contact with you. Most of polymers won't attack, won't
Okay,
make a allergic response, for example.
okay. And the
Okay.
second question, I don't know it's your field, but any comments or thoughts on photopolymers resins that might be good for skin contact?
Oh, I don't know much about photopolymerization, about photopolymer resins, but I think as I have seen one time, there's I think it's carbon 3D printing. It's like a commercial standard of uh, of the SLA process. I think it's carbon, the
SPL?
SLA, you know, stereolithography.
Yeah, I know SLA, but
Yes, they have a special type of resin that you have to print, and then you put in a kind of an oven to
okay.
finish the setting process. So
Okay.
I think if you're applying some thermoset resin in contact with the skin, the most thing you should be concerned about is to take out this non-reactant chemicals that stay in the end of the process. So you try to dry it, to take it out, to exudate it for the outside of the polymer. Then you can actually, I think, apply in contact with the skin, but I'm not certain. I should study more about it. And in the video that I talk here, 3D printing medical industry, they give
Okay.
many commercial grades of also vat polymerization resin. So I recommend this person. I don't know what's his name.
Eric Buba. I don't know if
Eric
I
Blum.
speak
I
right.
recommend they to see this video here of Go Engineer and take some of their grades or send an email to them if see some of their grades can be in contact with the skin, for example. Okay, this is my recommendation. I'm not so sure.
Okay, he said thank you.
Wow.
Something more you
No,
want to add?
no, just thank you for the attention. It was really fun to be here with you today. I was freaking out, nervous, but now I'm okay.
I
And
don't
I
know
hope you
why your
have learned
English is
something.
perfect. You look like
Oh, it's fun.
American. Yeah, your
Oh,
English is very
never.
perfect.
No, no, no.
Thank you very much for accept this invitation. I know it's very hard to be here, but thank you very much. And I will call you another time again because I
Okay.
really like the subject and I think it's a field who is just raising. So I think we can talk about this every time, every day. So thank you very much for coming. I really like you and I really like when you speak for us and everything. So thank you very much.
Well, thank you, Tainara.
Thank you
You're welcome.
everyone.
It was wonderful.
Ah, thank you everyone for watch and that's it. Bye bye. Thank
Bye
you.
bye.